Good morning, students, and welcome to our classes on statistics and mathematics. Today, we'll be discussing on another important topic called interval estimation. But this time around, we will be discussing interval estimation for the population variance. So, what we have today as the topic of discussion is interval estimation for the population variance. Interval estimation for the population variance. Interval estimation for the population variance. That's what we have today. Interval estimation for the population variance. We are going to approach this topic under two categories. The first category is interval estimation for one population variance. Interval estimation for one population variance. First category, interval estimation. Interval estimation for one population variance. One population variance sigma squared. And then the second approach is interval estimation for the ratio of two population variances. Interval estimation. The second one is interval estimation for the ratio. For the ratio of two population variances. Population variances, which of course can be written as sigma squared of x all over sigma squared of y. Or we can write it as sigma squared of y all over sigma squared of what? Of x. Ratio we mean here is the variance of a random variable x divided by the variance of the random variable y. Or it could be looked at as the variance of the random variable y divided by the variance of the random variable what? X. But particularly in this class, we are going to concentrate our effort in the first category, which is interval estimation for the one population variance sigma squared. That is what we're going to start with. So the first one, we are going to remind you certain certainties that we know in statistics. That first certainty is that it is known that if a random variable x1, x was 2, down to what? To xn, are random variables coming from a normal population. That is, it follows a normal distribution with parameters what? Mu and variance sigma squared. I repeat, if it is known that the random variables x1, x2 down to xn are coming from a normal distribution with mean mu and variance sigma squared, the following is true. That n minus 1 s raised to power 2 all over sigma whole squared follows a chi-square distribution with n minus 1 degrees of what? Of freedom. I will repeat. Or better still, before I even proceed to discussing the interval estimation for the one population variance, it is important that I tell my students the two key things that are needed each time we want to estimate interval for one population variance. So even permit me to clean here while I recall for you those steps now before we now begin to discuss this, so that the consistency in the discussion of the topic will be there. When we are talking about interval estimation for the one population variance. Those two key things that are needed are, number one, we need what we call the sample variance. What we call the what? The sample variance. We need the sample variance. Sample variance. And that sample variance is known as what? S squared. And then we need another thing. That another thing we need, number two, is what we call chi-square distribution. Chi-square distribution. Chi-square distribution. So the concern here is, how do we link the sample variance and chi-square distribution in the estimators of the intervals for one population what? Variance. Then what we are discussing earlier now becomes what? Necessary. And then I now remind you that it is said that if we have that x1, comma, x2, comma, down to what? To xn, are random variables coming from a normal distribution. That is, it follows normal with parameters what? Mu and variance sigma squared. These parameters, of course, are what we call the mean for the normal distribution mu and then the variance sigma squared. It is believed that n minus 1 s raised to power 2 all over sigma what squares follows a chi-square distribution with n minus 1 degrees of what? Of freedom. I will repeat. When x1, x2 down to xn are random variables coming from a normal distribution with mean mu and variance sigma squared, it is understood or known that n minus 1 degrees of freedom, or n minus 1 multiplied by sample variance all over the population what? Variance follows a chi-square distribution with n minus 1 degrees of freedom. This is what we call chi-square distribution with n minus 1 degrees of what? Of freedom. So what we are going to do is to use a sketch to show a chi-square distribution, and then be able to know how we can factor in this formula into estimating the interval for one population what? Variance. And look at what I mean by using a diagram. Let us say that I have a diagram that goes this way. A diagram that goes this way. This is a diagram. Or this is a line. And then in this line, I have something like this. This, of course, is a chi-square distribution because, of course, it is a skewed distribution. Skewed to what? To the right. Then let me say that I have the tails of this chi-square distribution from here to here, and then from here to here. So here is 1 minus what? Alpha, because the total area under any frequency curve must be 1 because it is a probability value. So if this center is 1 minus alpha, it implies that these tails, which are these shaded regions, becomes, here is alpha over 2, this shaded region equally, here becomes what? Here is equally alpha over what? 2. So at the moment you say alpha over 2 plus 1 minus alpha plus alpha over 2, you'll be able to arrive at 1, which of course is a probability what? Value. Let me call this line here what? A. Let me call this particular line here A. Let me call here A. And let me call here what? B. So by implication, the interval here A to B has a probability value of 1 minus what? Alpha. And of course, you remember that in interval estimation, 1 minus alpha is what we call level of what? Of confidence. So our concern now becomes, how do we now construct an interval that is going to bound our population what? Variance with 1 minus alpha degrees of what? Of confidence, or with 1 minus alpha level of confidence. Please permit me to clean it up while we now show the derivation on how we can arrive at that. So permit me to clean it up. Remember that each time we draw the chi-square distribution and we have here to be A and here to be B, that this our A is defined as. So we can say where of course our A equals chi-square of n minus 1 degrees of freedom of 1 minus what? Alpha over 2. That is how we define our A. And our B will now be defined as B is given as chi-square of n minus 1 of alpha all over 2. This is how we define our A and our B. Now we will first of all start by trying to construct a confidence interval for the whole of this. Here is 1 minus alpha. So what I'm now going to do now becomes that the probability, I have that the probability that this our A here is less than or equal to what? I have here to be what? N minus 1. Please permit me to put off my phone that is ringing. I'm sorry for that. So here is our n minus 1 or s raised to power 2 all over sigma whole square. Should be less than or equal to what? B, close the bracket now, which is equals to 1 minus what? Alpha. That is to say that the probability that this quantity lies between A and B is given as 1 minus alpha, where my A and B are as defined earlier here. Okay? So what else now? I am not interested in constructing confidence interval for this quantity. Instead, I am interested in constructing confidence interval for the sigma squared. So this thing becomes this way. That I have probability that our A, I want to remove this. I want to remove this n minus 1 multiplied by s raised to power 2. So what I'm going to do is to divide both sides with n minus 1 s raised to power what? 2. So what I have here becomes what? A all over n minus 1 all s what squared is less than or equal to what? 1 all over what? Sigma what squared, which is less than or equal to what? B all over n minus 1 s raised to power 2. Close the bracket. This is equals to 1 minus what? Alpha. However, we are not constructing confidence interval for 1 over sigma squared. That is 1 over variance squared. Instead, we are constructing confidence interval for sigma squared. So what am I going to do to this to make sigma squared to come up? I will now try to take the reciprocal of both sides. And taking the reciprocal of both sides, what I'm going to have becomes, of course, when we say reciprocal is 1 over that quantity. If you take 1 over this quantity, what you are going to have now becomes, if you take 1 over this quantity, you are going to have P of, this one will come up while this A will come down. So what you are going to have becomes, you have what? N minus 1 s raised to power 2 all over what? Over A. This sign is no longer going to be less than or equal to. It is going to be greater than or equal to. So we have greater than or equal to. Here, what you have is 1 over sigma squared. Because you are taking the reciprocal, it becomes what? Sigma what? Squared. Here becomes what? Greater than or equal to. What you have here becomes n minus 1 s raised to power 2 all over what? B, close the bracket. This becomes 1 minus what? Alpha. Now you see that our signs have changed. So I need to revert back the sign the way it was or the way earlier. So I'm going to begin from this. So this thing implies that what I have is this. This thing implies that what I have is probability. I will start from this one. That n minus 1 s raised to power 2 all over what? B is now less than or equal to sigma squared, which is less than or equal to what? N minus 1 s raised to power 2 all over what? A. Close the bracket. This is equals 1 minus what? Alpha. What am I going to do here? What I'm going to do here is very simple. Our interest is not looking at probability, we are looking at confidence interval. And you can see that sigma squared is what I have here. So the interval of the value is going to be this and this. Let me call those interval of values L and U. So I now have interval that L, comma what U, which is going to be interval that is going to bound the population variance from below, and interval that is going to bound the population variance from what's above. And that of below is what I have to be this. So this is equals. I have, here is my what? My n minus 1 of s raised to power 2 all over what? B, comma. This one becomes what we call n minus 1 of s raised to power 2 all over what? A. I will close it. So this is of course the interval which we need each time we want to construct an interval for one population what variance. And of course, where our A and B are as defined what earlier. So each time you are told to construct a confidence interval for one population variance, this is the lower and the upper confidence what interval for one population what variance. Where of course our A and B are as we have defined here. So we are quickly going to take one example and show how you can apply this straightforward. Okay? So let me read one example I have here. And that example says, and I write, that example says, okay? The example says, a random sample of size 20, a random, I call it worked example, okay? They say a random sample of size 20 from a normal population or a normal distribution has a mean of x bar equals 32.8 and variance s squared equals 20.34. They say construct a 95% confidence interval. Please permit me to write C.I as confidence interval for sigma squared. That is the question that they gave us. They say a random sample of size 20. This random sample of size 20 was drawn from a normal distribution. And the parameters of that normal distribution, or the observation that they got from that sample of size 20, is that the mean of that sample is 32.8. And then the variance of that sample, S squared, is 20.34. That we should use this information to construct a 95% confidence interval for the population what variance. And I have told ourselves earlier that each time you are told to construct the interval for one population variance, that the interval for one population variance is given as n minus 1 s raised to power 2 all over b, where this n stands for the sample size, this s squared stands for the sample variance, and this our b is as defined here. Then when we come here, n of course is the sample size, s squared is what is the sample variance, and then our a is as defined what here. So what we are going to do is to make use of what we have derived earlier now to apply whatever thing that we can deduce from this question. So it permits me to clean it up while we now begin to solve the problem together. So permit me to clean here. Permit me to clean here. Down to this place. Leaving only this one, which of course is what we are looking at. So our L and U here, as a way of solving it, I will say solution, solution. So what I have here is what? I have L and I have U. This equals. Here is N minus 1. My N this time around is what? Is size of what? 20. That's what they took. Size of what? Of 20. So I'll open a bracket this way. 20 minus 1 is 19. So I have 19 multiplied by. S raised to power 2, of course, is given in the question to be 20.34. Here is 20.34. Okay? Then I will say all over. Here is my B, and of course my B is given like this. Look at B here. Chi-square of this. So I have chi-square. N minus 1 here means 20 minus 1, which is 19 degrees of freedom. Our alpha here is 0.05 because here they ask us to control 95% confidence interval. So our alpha should be 0.05. And 0.05 divided by 2 is going to give me 0.025. So I have here to be 0.025. I will close it. Then I say comma. Here am I. Our n minus 1 here means 20 minus 1, which gives us 19 multiplied by. Our S here is still talking about sample variance, which is 20.314. You say all over. Our A here is what we have here, which of course becomes what? Our chi-squared of what? N minus 1. And this our n minus 1 means 20 minus 1 to give us what? 19. Then here is 1 minus half over 2, which is the same thing like saying 1 minus 0.025, which will give us, I think, either 0.975. Either 0.975. So this becomes our confidence interval for one population what variance. So the concern is, what is the true value of this chi-square of this degree of freedom, 19 degree of freedom, and the level of significance of 0.025. The value has been given to us here, so we are just going to call the value up. So this thing becomes, this is equals, we have 19 multiplied by 20.34 all over, comma, here is 19 multiplied by what? 20.314 all over. Let me call the value of this because it has been provided. The value of this one is given as 32.85, and the value of this one is given as 8.91. So we have it this way. It's given as 8.91. Okay? So permit me to equally clean here. When you divide the whole of this, what you are going to get is 11.7644. And when you divide the whole of this, what you are going to have is 43.3737. So these become the value of the confidence interval that is going to bound or contain our population variance sigma squared at 95% confidence interval. This is how to go about constructing the confidence interval for one population variance. Sorry for the little distraction that we had earlier when my phone, the other phone of mine, rang. I'm deeply sorry for that. We also recall for you that it's very necessary that you subscribe, like, share, and comment on our YouTube videos as we keep bringing for you classes that will change your understanding positively on statistics and mathematics. Thank you very much for your audience for today, and stay connected for our next classes.